So, first thing we're covering today, this is obviously a flashlight.
Oh wow.
That's my flashlight.
Is that a flashlight? No.
And I have a mirror. It's a flat mirror. In level physics, all we're doing is flat mirrors. And it says mirrors reflect light. We know what happens if I turn on my flashlight. It would turn on and then what? What's going to happen when that beam of light hits the mirror? It's going to reflect off, right? Okay. So I'm going to draw that. My light from my flashlight. It's going to hit here. It's going to bounce off. Because that's what light does on a mirror. Reflects. Okay, I'm going to label it reflection. Is it better? The light's a little dimmer. Is that better?
Lights off.
Off?
Yes. Yes.
Hold on.
No, yes.
Hold on. There's a light.
Yes.
Yeah?
Yes.
That's fine. I don't know. It's the other thing. No, it's not me. If I hear y'all snoring, though, I might accidentally lose a pen.
Lose a pen.
Yeah. I wouldn't test my aim. All right. On my lights. Because remember, hey, light exists as rays. So what we would call this ray right here, leaving the source, is called an incident ray. And don't get hung up here on the vocab because it's going to be really confusing. After it hits the mirror and bounces off, it's called a reflected ray. So we have an incident ray, we have a reflected ray. Reflected. All right. Images and mirrors are upright, virtual, and the same size. We look at mirrors probably most days. Some of us more than others. Your mirror should not produce an image that's upside down unless it's a curved mirror and you've got something funky going on. That image is virtual, and it's going to be the same size, again, unless it's one of those magnified mirrors that's curved. We do not study those in level physics, and you're welcome. Okay, so we have my incident ray, we have my reflected ray. That angle that the incident ray hits the mirror is my angle of incidence. And conveniently enough, the angle it's reflected, called my angle of reflection. My angle of incidence is going to equal my angle of reflection. So if I shine a flashlight at 30 degrees to a mirror, what angle is reflected? 30. If I shine a flashlight at 85 degrees to a mirror, what angle is reflected? 85. Makes sense, right? It's a little reminder that all electromagnetic waves travel at the speed of light, which is 3 times 10 to the 8th. You need to know that. All right, so that's reflection. Pretty easy. You know reflection. Angle of reflection equals angle of incidence.
Wait, what is that saying?
That just says C equals 3 times 10 to the 8th. That's the speed of light. And the speed of all other electromagnetic spectrum rays. All right. Reflection is bouncing off. What is refraction? Bending. Bending because different mediums. Okay, so I'm going to draw another beam of light, and I'm going to refract it this time. I'll do it in yellow. New beam of light, and it's bent. So in this case, it's hitting water. Refraction is bending. Refraction's bending of that light ray. Go ahead and label this one up here as air, water. All right, so different materials bend light at different values. You see this when you're driving at night and it's a clear night. Your headlights can just shine in front of you no problem. When it's foggy and now there's water particles in the air, your headlights don't work as well. You cannot see as far. It's because that light's getting bent at a different angle. We call this refraction value. And so each different type of object has a different refraction value. We're going to label those in. So this isn't like a dug out of a trench by someone who's underpaid and cleaned up and then sold for worth its value kind of jewelry. This is one that was made in a lab. But if I took it to a jeweler, they would take a small laser and they would shine the laser through the jewel, and the light would come out at a different angle. And they would basically put it on a protractor that measures that angle and see if this is actually a ruby or whatever it happens to be or not. Does that make sense? So we use this quite a lot. So if you want to see if your engagement ring is a diamond or a cubic zirconium, that's all that they do, is they would shine a beam of light through it, and how it's bent would determine what material it is. Cubic zirconia bends light differently than diamonds do. So if you know what you're looking for, you can tell pretty quickly because the way it's going to refract that light. So let's say a beam of light, so like a ray, in air, hits water at 47 degrees. What angle is refracted? What angle is it bent? Well, I said that different materials bend light at different values. We know the values that it's bent. For instance, air is 1.003 and water 1.33. Do you have to have those memorized? No. I ask that you memorize the speed of light, know that it applies to all electromagnetic waves, and you've had to memorize gravity. That's about it. So to figure out at what angle it's being bent, you use a formula called Snell's law. Snell. Snell.
Is that 1.003?
Mm-hmm. So this law looks like that, and it looks a lot more complicated than it is. So just write it down, then we're going to talk about what all that means.
Oh, no. Is that I?
It is. So what this means is that the angle of incidence's refraction value.
Is it negative spin?
Nope, that's just the times. times the sine of its angle of refraction equals angle of the refraction value of the second medium times the sine of its refracted angle. So we're going to do it. We're going to actually do 2. It's not as bad as it looks. All right. Using my example problem. It says a beam of light and air hits water at 47 degrees. What angle is refracted? Ni sine theta I equals Nr sine theta R. Okay, all I did was I rewrote my formula. I'm going to fill in the values that I gave you. So my angle, my incidence, in this case, because Ni is going to be for my incidence, is going to be air, because that's the first thing it's going through. So 1.003 sine of 47.
Wait, can you, do the graph a little bit, please?
That is going to equal 1.33 sine of my unknown refracted angle. The first thing, because I appreciate y'all getting out your calculator to start punching in numbers. Turn on your calculator. Go to mode. We need to make sure you're still in degree. So hit mode. If your degree is not dark like this, move down, make it flash, and hit enter. So I put it in degree mode. And then you can second mode to quit. I want it in degree. All right. So I'm going to solve for this part first. 1.003 sine of 47. 0.7335477627. That's a lot of numbers, right? So I'm not going to use my rounded values that I'm writing down here because it's rounding my number, but I want you to be able to follow my math here. I want to get theta by itself. So the first thing I'm going to do is I'm going to divide both sides by 1.33. So I have this number here. It's a super long number. I don't want to mess with it, so I'm just going to hit divide 1.33 and hit enter. Now I have 0.552-ish equals the sine of that angle. But I want that theta by itself. So I need to use the inverse of sine over here. I need to get rid of that sine. So we're going to hit second sine, second negative. What that's going to do, second sine, not that, second sine gives me the inverse of sine. Then if I page out a little bit, second negative puts my answer from the last problem there. So I don't have to type it all back in. And then you hit enter. Theta is equal to 33.47 degrees.
Whenever I did that, it said error. Oh, it's
So when I'm trying to get rid of that sign so that theta's by itself, I have to use the inverse of sine to cancel it out. That's all I'm doing.
Yeah, and then like the theta has an R with it.
Yes, that's the refracted angle. So I'm keeping it different from my incidence angle.
Okay.
Amethyst is purple, I think, right? So I have a piece of amethyst and I put it and I submerge it in water. All of it's water. And I shined a light ray through the water. It's going to hit that amethyst and refract. So my refraction index of my water, 1.33. The angle I'm shining that laser through in the water, the angle of incidence, let's say it's 50 degrees. It's not because I can barely draw straight lines, but this is where we're at. And it gets refracted an angle of 28 degrees. What is my refraction value for amethyst? In an ideal world, I'd change my numbers to look it up, but I've used a different color Joel every time, so. So, first steps again, fill in what you got. So, Ni sine theta I equals Nr sine theta R. That's Snell's law. 1.33 sine of 50 equals Nr times the sine of 28. And then you would start simplifying what you can to get your N by itself. Bless you. So I would go 1.33 sine of 50. 2 equals NR times sine of 28, which is 0.47. And again, I'm keeping the values in my calculator, but I'm not going to write them all out here. So I would do 1.018839109 divided by that sine of 28. To give me a refraction index of 2.17. That is actually zirconius and not amethyst, but you get the point. On the test, which is Tuesday, there is one problem like this. It will have the formula on there, and it has labels like this. It's not going to be a word problem. It is labels like this. Okay? You get half credit for filling in the formula correctly. So even if you've completely messed up on an inverse of sign and you can't figure out you're getting an error, half credit just for being able to plug in onto the formula. Okay? What time is this period in? 23. Okay. I'm going to assign you an assignment, and you're going to start on it today. We're not going to work on it tonight because we're going to have time tomorrow in class to finish it. It's going to be in the Google Classroom. This is third period. Classwork. Blanket. So, Snell's Law Practice is a Google form. I want you to be working through these so that when you come and you're doing it and you're getting an error, I can fix it. The only way I can do that so I can show you what's going on with it is if you actually do it. I cannot help you if you're not doing it. It's one of those things. So please make sure you are doing it so I can help you.